Cool. Let's get started. Hi, everyone. Welcome to this talk on lessons learned migrating the Maps SDK to Compose. My name is Chris Arriola, and I'm a developer relations engineer on the Android team working on Compose. Before I was on the Android team, I worked on the Maps team, where I worked on a library called Maps Compose. It's a Compose interop library for the Maps SDK. So I had a lot of lessons learned in API design with composable functions, and that's what I want to share with y'all today. But why am I talking about this, and why might it be relevant to you? When building Compose apps, you quickly realize that you end up building a library of components. So you also become a library developer yourself. So I'm hoping that the lessons I learned here will apply to the library of components that you're building. Nice. So since Compose 1.0 was released last year, a common question that we get is, should I use Views or Compose? Same diagram that Florina shared yesterday. And the short answer here is that your first go-to should be Compose. So try to build your UI in Compose, and when it doesn't work or it's not there yet, then that's when you would use Views. And the Maps SDK falls under this path in the decision tree. So Maps SDK is view-based, and if you want to use it in Compose, you have to use one of the available interop APIs to bring it into Compose. So what are those interop APIs? The most common one is Android View. It's a composable function that allows you to bring a view inside Compose. So it accepts a factory lambda. So this would be invoked once when the composable function enters the composition. So here, this is where you would construct your view. And then it also accepts an update lambda, which would be invoked when the view has been inflated and is part of the view hierarchy. So that's where you would mutate your view and set it so that it displays the state that you want. The cousin of Android View is Android View Binding. So this requires that you have view binding enabled on your app. And with Android View Binding, you would call inflate on the generated binding class from one of your layouts. So for example, say you have map layout.xml, you would call map layout binding.inflate in your factory function, and then in the update lambda, that's where you would get your inflated views. And then that's where you would mutate it. So before Maps Compose was available, one of the most common integrations that we've seen from developers when they're trying to add the Maps SDK to their app is through using Android View. So to add maps, you would create a map view instance in the factory lambda, and then in the update lambda, that's where you would call getMapAsync to asynchronously get a handle to the Google Map object. Once you have that object, you can add markers, add circles, do whatever you want on the map. And in addition to that, the map view requires that you invoke lifecycle methods when the lifecycle owner undergoes lifecycle events. So if it's an activity or a fragment undergoes onCreate, you want to call onCreate on the map view, and so on. And how you would propagate those lifecycle events is by creating a lifecycle event observer. When you receive the event, you pass it to the map view, and then you would add that observer to the lifecycle. And then that code would exist within a disposable effect, composable function, so that you can remove the observer when the underlying composable function disposes. And all that code, right, the Android view and the disposable effect view, or disposable effect, would be contained within a composable function. Let's call it MapViewContainer. And that function can accept parameters that you can then pass to the map, right? So in this case, we're taking in a single parameter, lat long, to display a marker on the map. And this implementation is precisely what Crane, one of our sample apps, this is precisely how it was implemented. It was a pretty simple use case where it only displayed a single marker on the map, and it also allowed you to control the zoom level. But what if you wanted to do more things on the map? Like, what if you wanted to add multiple markers? So we can refactor our function to accept a list of items instead. But the implementation gets a little bit more complex, right? Because we have to remember the previous set of markers, and when this recomposes, we want to do a diff between the new set of markers. And based on the diff, you either add, remove, or update markers. And kind of extending that logic even further, like what if you wanted to add circles or polylines, polygons? What about custom info windows, click events? So there are a lot of things that you essentially have to wrap. And it's not the best developer experience, right? So I'm curious, who here in the audience had to write code like that with Maps SDK? Yeah, a few people. So wouldn't it be great if there was a library that handled all that code for you? And that's precisely what Maps Compose is. It's a Compose interop library for the Maps SDK that handles all the interop code that I just showed you so that you can use a composable function instead. So forget about what I just showed you. You don't have to write that. You can just add this library and use composable function. So what are the features of this library? So this is how you would add a map now with Maps Compose. You call the Google Map composable function. You pass in a modifier, like fill max size to occupy the maximum allotted space. And this function accepts a composable function lambda, where you can invoke child composable functions like marker to add a single marker. Since marker is a composable function, we can use standard Kotlin syntax to invoke it multiple times to add multiple markers on the map. The camera controls on the map can be done by state hoisting a camera position state object. Here you would call remember camera position state, specify the position on the map that you want to focus on, and then pass that object to the Google Map composable function. Camera position state also has support for moving the camera, so you call the move function and then pass in a camera update to move the camera from one place to another. And it also supports animating the camera position from basically smoothly transitioning the camera position. And this is a suspending function, so you have to invoke it within a coroutine scope. So that was a quick walkthrough of Maps Compose and a background of how it came into be. Let's transition to what are the lessons in composing APIs. So the first one is to think declaratively in Compose. And this is perhaps the most important mental model shift when learning how to build apps with Compose. And understanding this has implications in how you think about designing your APIs. So as a quick refresher, Compose at a high level works by converting state into UI. And if you want to update your UI, you have to change the state, which causes recomposition, and then that regenerates your UI. There's actually a really great page in our docs called Thinking in Compose that goes over this mental model of how you can think declaratively in Compose. Definitely recommend checking this out if you haven't already. So, if thinking declaratively is what we want, what does it mean to not think declaratively? And a question that came up when Maps Compose was released was this. How can I call clear on the map? Because this feature wasn't supported in Maps Compose. And clear, for context, when you invoke it, it removes any drawn objects on the map. So any markers or polylines, those are all removed, and you just have your base map. So in Compose, how you would do that, right? Just kind of thinking about the diagram earlier, if we want to clear the map, we want to change the state such that when it recomposes, no drawn objects are visible on the map, right? And one way to do that is to wrap the composable function lambda that you provide in the Google Map in an if statement. So if that's false, then nothing is drawn on the map. Okay, so how does this principle translate in API design? So let's look at markers specifically. And I hinted at this challenge earlier, implementation challenge earlier. So what if the composable function accepted a list of markers instead? And I mentioned that you have to essentially remember the previous state, add, remove, or update based on the diff when things recompose. And if we think about this a little bit more abstractly, the behavior of adding, removing, and update, right, changing this essentially tree over time is precisely what Compose is great at. So can we use Compose to better represent this API? So map, if we think about it from a tree perspective, a map is the root of the tree, and it can have many markers as child nodes. So taking this model, we can then convert marker as a child composable function instead. And this is precisely the design of Maps Compose right now. So with this approach, we can tell the framework, Compose, what markers are in and out of composition. We can also use Kotlin control flow and conditionals to essentially conditionally determine which markers we want to display on the map. And we don't have to remember the previous state anymore. Compose handles all of that for us. So to implement this API, the marker composable function emits a compose node. And this implementation creates a subcomposition that manages the marker's state instead of compose UI nodes. So what does that mean? It's a lot of jargon. So to use compose node, you have to provide it two types. The node type, in this case, it's a marker node and an applier. And I'll talk about the applier in a second. So this composable function accepts a factory. In the factory, this gets invoked when the composable function enters the composition. So in this case, that's when we want to add the marker. And then this marker is then wrapped in our node type, which is the marker node. And this compose node also accepts an update lambda. So this would be invoked when the marker composable function recomposes. So we can provide code here that would explicitly run when one of the parameters changes. So for example, if the title changes, we can update the underlying marker's title. So I'm just displaying the title here, but the same pattern applies to any parameter that the marker composable function accepts. So I mentioned applier, and this node is of type map applier, and an applier is essentially an interface that receives tree-based operations during composition. So as nodes are removed, added, or moved, then we can listen to these events and essentially perform the right operation. So in this case, right, if the marker leaves the composition, we can then remove the marker. So I've been talking about marker a lot, but this same design applies to other drawn objects on the map, like circle, polyline, and polygon. Cool. So that was the first lesson. The next one is to reuse as much as possible. The Maps SDK has been around for over 10 years. And if you are familiar with using the Maps SDK, then using the Maps Compose should feel really similar. And one way to do that is to reuse as much as possible in terms of classes and types, but of course, deviating where it makes sense. And one way this principle manifested is through updating the camera position. So to update the camera position on the Maps SDK, you would create a camera update object from the camera update factory class. And then you would take that object and pass it to the map by calling either move camera, or if you want to animate the camera position, you call animate camera. I mentioned in Maps Compose, the camera is controlled through this state-hoisted camera position state object. So in Maps Compose, you can use the same object, the camera update object, but instead of passing it to the map composable function, you would provide it to the camera position state object. So you would call move or animate. So notice I said reuse as much as possible. There were some instances when reuse wasn't possible. So there's this class called UI settings in the Maps SDK that controls different UI settings on the map, like if the compass is enabled, if the toolbar is enabled. And you can't actually construct an instance of UI settings. You only can obtain it when the map has been inflated, and once you obtain a handle to the Google Map. And going back to the first lesson, right, we want to be able to declare ahead of time what our UI settings should be. So we can't reuse this class in this case. So Maps Compose introduces a wrapper class, map UI settings, which essentially mirrors the same properties in UI settings. So you can create an instance of this map UI settings and then provide that to the Google Map composable function. A related point to this is the Google Map has certain properties that you can mutate at runtime. And like if the buildings are enabled on the map, if the My Location blue dot is enabled, and a very initial design of the Maps Compose, of the Google Map composable function, exposed these properties as parameters to the Google Map composable function. But there were a lot of these properties, and it's really affected the usability of this function. So I don't think there's really an optimal number of parameters that you should strive for, but in this case, we can improve it by wrapping related properties into a state holder. So that's precisely what map properties is. It contains these related properties that can be changed on the map, and you can create an instance of it and pass it to the Google Map composable function. Cool. So the next lesson is to use Kotlin features. And this might be obvious to you if you're already fluent in Kotlin and can write Kotlin in your sleep, but there are a lot of Java-based apps and libraries out there. And thinking in Java is quite different from thinking in Kotlin, and Compose is entirely written in Kotlin, so you should really lean in these Kotlin features. What are those features? To mention a few, extension functions are prolific in the Compose library, so modifiers use this a lot. Default parameters, a lot of composable functions provide defaults, so you can use them easily without providing that many arguments to it, or you can customize it as much as you need. Lambdas are used by layouts like row, column, box, and then, of course, coroutines are used to perform asynchronous operations. There's a really good page in our docs called Kotlin for Jetpack Compose that kind of enumerates all the idioms that are commonplace in Compose. Definitely recommend you check it out. So which Kotlin features does Maps Compose use? So default arguments are used by the Google Map composable function. You can pass in arguments if you want, or you can call it without any arguments. It's not a very useful map, but you can do that if you want. Trailing lambdas. So trailing lambdas are used for layouts in Compose, and a layout is basically any composable function that accepts a composable function lambda as a parameter. And typically how you would use layouts is you would use it through this trailing lambda syntax, which is much more concise versus having to name the content lambda and having that part of your function parentheses. So while you can definitely call it with content equals lambda close parentheses, the preferred syntax here is to use trailing lambdas. And then Maps Compose also uses coroutines. So I mentioned animating the camera. This is implemented as a suspending function, even though the underlying Maps SDK implements this as a callback-based API. So you would have to invoke this function within a coroutine scope. And the advantage of this is that if you had to perform, a sequence of asynchronous events or a sequence of animations, you can do it in a much flatter syntax versus having to nest callbacks. Cool. So The next lesson is to stay consistent with Compose Toolkit APIs. And what I mean by that is it's best to abide by the same principles that the Compose Toolkit APIs are designed with, because inconsistency is quite jarring when we encounter it. It causes us to stop and think, and consistency, on the other hand, we don't notice it when it's consistent because it just works the way we expect it to. So that's essentially what we're trying to strive for here. So how can we be consistent? One way is through vocabulary. So composable functions that return unit or don't return anything are capital case, uppercase Pascal case. So we say capital G Google Map and not lowercase Google Map. Composable functions that return unit are also nouns. So just Google Map, not verb, noun, render Google Map. And then composable functions that return values just follow the standard naming conventions for methods. So the special case here is that if the function remembers something, then you want to prefix it with remember so it's clear to the caller that this has implications in terms of caching state across recompositions. So we can also be consistent by providing predictable parameters. So composable functions should accept a modifier as its first optional parameter. And the advantage of that is that you can take advantage of the rich set of modifier APIs to decorate and augment your composable function. And if it's the first optional argument, you can also provide it as an argument without naming the modifier argument. And then the other predictable parameter here that I mentioned is that if it's a layout, you want to enable this trailing lambda syntax, and how you do that is by providing the content composable function lambda as the last argument to the function. So again, you can call it by naming content if you want, but the preferred syntax here is this trailing lambda syntax. So these are just some examples of how you can be consistent. There's actually an entire page about API guidelines for Jetpack Compose. This applies to libraries and apps, so definitely check it out. It's something I reference heavily while working on Maps Compose. All right, the next lesson is to use Compose common types, because Compose introduces a handful of types and classes that might better represent a given piece of data. So for example, the Maps SDK has this marker options class, and so you would construct a marker options when you want to add a marker to the map. And one of the supported features for marker options is this anchor function. It's a bit hard to see, but it accepts 2 float values, and that determines the marker image's relative position to the position of the marker. And Compose introduces this offset value class, which I think provides improved semantics. So it's clear that this anchor is an offset in Cartesian space and not just like some raw float values that we're passing. And one of my favorite applications of this lesson is actually pertaining to color. So there are certain objects that you can configure the color of. So circle options, for example, you can change the fill color of the circle or the stroke color. And on the Maps SDK, this parameter is represented as a color integer. But Compose actually introduces a color value class. So if we expose and use color value class from Compose, the advantage of this is that if we're using material theming, then when the system appearance changes from light to dark or vice versa, we get the color updates for free, which is really nice. And the last lesson I want to share, which admittedly might be very Maps Compose specific here, is to provide an escape hatch. So what do I mean by that? The Google Map object is entirely managed by the Maps Compose library. And this is necessary, right? Because Maps Compose performs the marker additions and the mutations on the map, so you don't have to do that directly. And one of the consequences of leaking this Google Maps SDK object is that it might conflict with the operations that Maps Compose is doing for you. So the 1.0 version of Maps Compose actually didn't expose that. But there's a popular companion library to the Maps SDK called the utility library that provides additional features to the map, like marker clustering, heat maps, icon customizations, and so on. So there was a lot of developers mentioned, hey, how can I use this with Maps Compose? And while Maps Compose should eventually support these features, it doesn't yet. So that's where the escape hatch comes in. So there's a need to obtain the Google Maps SDK object and use it alongside the utility library. So a subsequent version of Maps Compose actually exposed the Google Map composable, object from the Maps SDK. And how you would obtain that is through this map effect composable function, and that gives you a handle to the Google Map object. There's appropriate guardrails to prevent misuse of this API. So, for example, you have to explicitly opt in to this experimental API, because the goal is that this will eventually be removed, and you can, perform clustering and heat maps and so on, all natively in Maps Compose. Cool. So those were all the lessons. I wanted to share some limitations of Maps Compose, because at its core, Maps Compose is an interop library for a view-based library. So there were some limitations on sort of providing like a Compose pure API. And the first limitation is that Google Map is not stateless. A good litmus test for a stateless composable function is that you should be able to provide the same state object to multiple composable elements. So if you wanted to create two different maps, you should be able to pass in the same camera position state to these two different maps to control, so you have a single point of control for these two views. But unfortunately, that's not allowed right now. You'll get an exception if you try this, because the Maps SDK object actually manages the camera. So there's a constraint where there's a one-to-one relationship between the camera position state and Google Map composable function. So if you wanted to use two Google Map composable functions, you have to provide two separate camera position state objects. And the last limitation I ran into is that there were some properties on the map that can't trigger recomposition because they have to be provided once to the map view object. And one example of that is the map ID. And map ID is a unique identifier that allows you to actually restyle the map on the cloud. So since this has to be provided once, the pattern that Google Map composable function implements is this factory lambda. We've seen factory lambdas quite a lot. So this would be invoked once when the composable function enters a composition, and then that provides a property to the map. But in a Compose sort of native world, this map ID should be configurable, and it should trigger recomposition. So to summarize, think declaratively in Compose, reuse as much as possible, use Kotlin features, stay consistent with Compose toolkit APIs, use Compose common types, and provide an escape hatch. So here are some resources if you want to learn further. There's a link to Maps Compose. Definitely check out our code labs if you want to learn a specific topic in Compose. Our samples, I mentioned Crane, but we have a bunch of other samples you can check out. And then, of course, our docs, which is a great resource. On that note, it's time to migrate to Compose. I'll be here answering questions. If you have any questions about migration, libraries, apps, talk to me. Thank you.